We recently have added a simple function interface for aggregation functions. It has been adopted by a few people. So today I would like to give a formal introduction about this interface to the broad audience at VeloxCon. So the first question you may have in mind is, there is already a way to implement aggregation functions in Velox. So why do we need a new interface? Well, so let's look at how much code the author would need to write for one user-defined aggregation function, or we call it UDAF. With the existing interface, the author needs to implement 8 required methods. And then depending on the properties of the accumulator or whether the author wants their own two intermediate logic, they can also implement 6 optional ones. So there are 2 problems with this existing API. So one is that some of the methods, they are slightly different, but still similar. For example, the add row input and add single group row input. So that requires the author to be familiar with what's the relationship between those 2 methods and what's the difference. Another issue is that those methods, they either take vectors of input or they produce vectors of result. So that requires the author to be responsible for handling all the arbitrary encodings of the vectors and also the internal representation of the vectors of the nested compact type vectors. So we look at the size of 3 example aggregation functions, the average, array and the positive distinct. We found that the size of those functions using the existing API takes about 211 to 357,000 lines of code, and that's the function body itself, not including the registration code. So those numbers doesn't seem too large, but if we look at how many UDFs the author needs to write, in Presto there are 91 distinct aggregation functions, and in Spark there are 65. And we know that we have been aware that in some use cases, we may want the end users to be able to implement their own custom UDAFs to be used with their queries. And in that situation, even more UDFs will need to be implemented. So those add up to be a lot of code. And also remember that the end user are usually not Velox experts. Therefore, we introduced this simple UDF interface with the goal of reducing the amount and complexity of the code that the UDF author need to write. So with this simple interface, the author implements a constructor of the accumulator type plus 4 core methods to process the data. Optionally, when needed, the author also implements 2 other methods, the 2 intermediate and destroy. The best thing about this simple interface is that those methods either take a single row of input or they produce a single row of results. So the author no longer need to worry about the encodings of the vectors. So let's look at what's the simple UDF interface look like with an example of array. Array is an aggregation function that take input of arbitrary type and produce an array for each group with the input values as the elements in the array. So first we define a class, simple array aggregate, and then we declare the input type, the intermediate type, and the result type. So here we use the generic T1 to represent the arbitrary type T. And then notice that we wrap the input generic T1, input type generic T1 inside a row type. So that is required by the simple UDF interface, even if there is only 1 argument, because it make it easier for us to infer the number of arguments of the function. And then the intermediate type and the result type are pretty straightforward. They are just the array of generic T1. So the next thing is a critical decision that the author need to make. Whether this aggregation function has a default no behavior. So what does it mean? We found that for most of the aggregation functions, they ignore the input rows or intermediate rows when there is the no value at any of the column. Plus, they return the nodes as a result if they return the nodes as a result for the groups that has no rows or only that has no input row, or only the no rows that has been ignored. An example is that query where all the input rows are null and those are ignored. So the result is also a null. So that is the behavior for most of the functions. So we make this default null behavior to be true by default. However, for the array function, it actually doesn't follow this behavior because if there is an input value that is null, we actually want to add the null as an element in the result array. Therefore, in the class that we defined, we overwrite this default null behavior flag to be false. And then the main part of the function is the accumulator type struct defined in the UDAF class. In this struct, we declare some properties about the accumulator, whether it's a fixed size, whether it uses external memory, and whether it is aligned. Those flags also has a default value, so the author only overwrites them if they don't want the default one. And then the author defines the accumulator type constructor to indicate how they want the accumulator object to be initialized. Similarly, the sum of the accumulator may require a special cleanup when they are destroyed. So if that's the case, the author also defines a destroy method to do that. So now let's look at the core part of the aggregation function. That is the four core methods in the accumulator type. The add, combine, write intermediate result, and write final result. Due to the limited time, I will only talk about those methods for the non-default null behavior functions. For the functions that has a default null behavior, actually the function signature for those methods are slightly different, and we have a documentation that explains very well about those details, so you can look it up. So for the array function, it has non-default null behavior. So the first two methods, add input and combine, they take a single row. They take a row of the input arguments, or they take a row of intermediate state, and then they add the values in those rows to the current accumulator. And then these two methods return a Boolean indicating whether this call update the current accumulator. If an accumulator has ever been updated by add input or combine, then we set an internal state of the accumulator to be a non-null group. That is the flag that you can see received by the write intermediate result and the write final result. So those two methods, the last two methods, they receive a flag indicating whether the current accumulator is a non-null group, and then they write the content in the current accumulator to the out arguments and return a Boolean indicating whether they have written a non-null value to the out argument. So this is what those functions do. So for the array add example, the add input method is pretty simple. Regardless of whether the input value is null or not, we always append it to the current accumulator, and we return true means that we have updated the current accumulator. For the combine method, it takes a single input intermediate state, and it wants to merge that into the current accumulator. So this method, it first checks whether that other intermediate state is null or not. If it is null, then it represents an empty accumulator. So in that case, we don't need to do anything. We don't need to update the current accumulator. So we just return false. If the other intermediate state is not null, then we add all the elements in it to the current accumulator and then return true. The write intermediate result and write final results methods for array are pretty much the same, except the method name. In these two methods, we first check whether the current accumulator is a non-null group. If it is not, if it is a null group, means that this accumulator has never been updated by add input or by. In that case, there is no value in the accumulator, so we return false, means that we want to write a null as a result for the current group to the out argument. If the current accumulator is not if the current accumulator is a nano group, then we copy the list of values in the accumulator to the out argument that is a rewriter in this equation. And we return true means that we have written some nano value to the out argument. There is one last optional method that the author can implement. It's called toIntermediate. So it is useful in this case. When the grouping keys of an aggregation function, when the grouping keys of an aggregation operation has very high cardinality, the partial aggregation step cannot reduce the data size. So it's not very helpful to do that. In that situation, VLOS has an optimization called the abandoned partial aggregation step. In that optimization, instead of doing the aggregation as the partial step, we actually convert every row input value into an intermediate state to be aggregated together as the final aggregation step. And this toIntermediate method is used to do that conversion. And this toIntermediate method is the optional one, because if the author doesn't implement it, then there is the default implementation of the toIntermediate that will be used. But the default one might be less performance, because the default implementation will add every row input value to an accumulator and then extracts the accumulator to the intermediate state. So there is one more translation that sometimes can be expensive. And excuse me. Yeah, okay, thank you. So that default implementation might not be efficient, and if the author cares about the performance, then they can implement their own toIntermediate method. So due to the limited time, I will skip the detail of this method. So basically, what it does is that for an input argument, it produces an array that's sorry. It produces an array of size 1 with that input argument as the single element in it as the intermediate state of it. So now let's register this aggregation function that we just implemented. We currently use the same registration API that we have been using before. And the only difference is that instead of using the UDAF class as the type of the function instance, we wrap it inside a simple aggregate adapter and use that together as the type of the function instance. So there are 3 limitations today with the simple aggregation function interface. The first one is that it currently doesn't support a function level state outside of the accumulator, which is sometimes useful, especially for the decimal related aggregation functions. There is a work in progress from the open source community to help us address this limitation. And another limitation is that it doesn't support optimization on constant inputs. For example, sometimes the author may have a sense that a particular argument to the aggregation function might always be constant. In that situation, they can add a faster path for the constant input to read that constant value only once for the entire batch. That is currently not supported in the simple UDF interface. And then the third limitation is that the simple UDF interface doesn't support the aggregation pushdown yet. So if anyone has interest to help us address those limitations, please reach out to us, and we are happy to collaborate. So with the simple UDF interface, the size of the average and the react function reduced from 357 and 211 to 66 and 106 source lines of code. We have also compared the performance of the simple implementation of those functions versus the existing vector-based implementation. We found that for the average function, the performance of the simple implementation is approximately the same as the regular implementation. on the flat and the dictionary encoded input. The simple implementation on constantly encoded input is slightly slower. This is because the regular vector-based implementation of average function thus has a faster path for the constant encoded input. So this is due to the limitation that I just mentioned. For the reg function, the simple implementation is always approximately the same as the regular implementation on all the flat, constant, and dictionary encoded inputs. So with that, we conclude that the simple UDF interface can effectively reduce the amount and the complexity of the code that the UDAF author need to write, while at the same time that does not sacrifice the performance for most of the case. So we already have some people tried it out, and I generally got positive feedback. So we would like to invite the community to please try out this simple UDF interface and let us know if you have any feedback that you would like to share. So finally, I would like to thank my colleague Liz for helping with the design of the simple UDF interface. I would like to also thank the early adopters from the community, including Liu Jiayi, Xu Mingming from the open source community, and Eric and Masha, who added our meta internal functions using this simple interface. So they have adopted this simple interface, and they also share the feedback with us. So I would like to thank these first heroes who are willing to try out this new thing. So finally, I would like to especially thank Liu Jiayi from the open source community who help us extend the simple UDF interface to allow the function level state. So with that, I conclude my presentation, and I'm happy to answer questions if there are any.